Students, in this session we will do a problem on controllability and observability. And here we will check the controllability and observability using both by Kalman's test and by Gilbert's test. Question is, write the state equations for the system shown in the figure in which x1, x2 and x3 constitute the state vector. Determine whether the system is completely controllable and observable. So you are given a block diagram. In that it is clearly marked the different state variables that are x1 of s, x2 of s and x3 of s. That means here the Laplace transform version of the state variables is given. So the question, it is shown that the state vector is constituted by x1, x2 and x3. So now you have the Laplace transform of the state vector in the diagram, okay? You have to determine the controllability and observability. You know that to check the controllability and observability you have two steps. That is, either you can check it by Gilbert's test or by using Kalman's test. Here, for the familiarity with the Gilbert's test and with the Kalman's test, the problem is doing in both ways. So you know that the procedure, first of all you should go through the Kalman's test procedure and Gilbert's test procedure, then only you can solve the problem. And in both the tests you need state model of the system. So bear in mind that you have to first find out the state model of the system, okay? Both tests start with the state model, that is x dot of s is x dot equal to a into x of t plus b into u of t. Similarly, y equal to c into x plus d into u. So that is the equation that you are going to start with. So you have to derive that equation from this block diagram, okay? That is your first step. So you need here there are three state variables, so you need x1 dot, x2 dot and x3 dot equations. So first of all let us go to this block diagram. In this you know that at the output side there is x1 of s. So x1 of s will got some equation. What is equation for x1 of s? It is obtained by multiplying this with this sum term, right? That is x2 of s minus x3 of s into 2 by s into s plus 1 equal to x1 of s, right? Just to look at this block diagram and find out the equation, okay? x1 of s is obtained by multiplying this block with x2 of s minus x3 of s. Similarly, what is x3 of s? x3 of s is obtained from x1 of s multiplied by s, okay? How will you get x2 of s? x2 of s is obtained from 2 by s plus 3 multiplied by u of s minus x1 of s. So you can write the equations. See, first of all you are taking the x1 of s. How will you obtain x1 of s? That is shown here. That section is isolated here, and you can write the equation x1 of s equal to x2 of s minus x3 of s into 2 by s into s plus 1. So here you have to make some necessary arrangements. That means this term can be multiplied. You can multiply the bracket terms and the denominator can be taken to this side. So you will get the equation as s square into x1 of s plus s into x1 of s equal to 2 into x2 of s minus 2 into x3 of s. Here I am not explaining all the steps because it is all simple mathematical procedure, that is simply multiplying and simply rearranging the equation, okay? So next, here we will get a Laplace transformed equation and the variables are x1 of s, x2 of s and x3 of s. But what is your aim is, you need to find out the state variable equation, that is x3 dot, x2 dot, in terms of x3 dot and x2 dot. So you have to first convert this s domain equation into time domain equation. So you have to take inverse Laplace transform of this equation. See, here we are assuming that initial conditions are equal to 0. So you can directly write s square into x1 of s, inverse Laplace transform of this equation I am taking. So s square into x1 of s constitute, you know that d by dt of x is equal to x by s, that is its Laplace transform. So here it is given that s square into x1 of s, that means it is a second derivative. Inverse Laplace transform will be second derivative of x1 of s. So that you can write it as x1 double dot. Similarly here it represents inverse Laplace transform will give you first derivative. So you can write x1 dot. Here you can write 2 is a constant, x2 of s inverse Laplace transform will be x2. Minus 2 into x3 of s, its inverse Laplace transform is minus 2 into x3. So this is your first equation. You can notate it with a 561 here. So again you can go to this block diagram, and here you are representing the x3 of s. You can see actually you are writing the equations for each and every state variable. Now up to this we have derived the equation for x1 of s, and we have written the time domain equations. Next we have to go to x3 of s. What is x3 of s? x3 of s is obtained by s multiplied by x1 of s, that is drawn here. x3 of s is equal to s multiplied by x1 of s. Okay, here also you have to find out the inverse Laplace transform equation in order to write the time domain equations. You can directly write here, that is inverse Laplace transform of x3 of s is equal to simply x3. Inverse Laplace transform of s into x1 of s is x1 dot. Okay, so that is your second equation, that is notated as 562. Next you have to go to the block diagram, and you have to derive the equation for x2 of s. It is obtained by multiplying this gain by u of s minus this quantity. Okay, that is x1 of s. See the block diagram here. x2 of s is equal to u of s minus x1 of s into 2 by s plus 3, that is written here. You can also multiply the bracket terms with the gain products, and you can rearrange the equation, so you will get the equation like this. Here also you want to find out time domain equation, so you are taking the inverse Laplace transform of this equation. So you will get x2 dot plus 3x2 plus 2u minus 2x1. See here, actually this is the s domain equation. By taking the inverse Laplace transform you are getting the time domain equation, and here whenever a s domain quantity is multiplied by s, then its inverse Laplace transform will be first derivative. Okay, whenever it is multiplied by s square, then inverse Laplace transform will be second derivative. Here it is first derivative, that is why we are writing the equation, that is x2 dot will be equal to this one. So you can directly get the x2 dot equation from this equation, right? You can rearrange this equation as x2 dot will be equal to minus 2x1 minus 3x2 plus 2u. Okay, so these are the three equations. So you have 561, 562 and 563. You need x1 dot, x2 dot, x3 dot form. So x1 dot is x3, that you can directly write it this from this equation. Here x2 dot is equal to this equation, and next you want x3 dot equations, but here you don't have x3 dot equation, you have rest of the term is this one. So you need to find a x3 dot equation. So here you are taking from the equation 562, see this is equation, here you can write x3 will be equal to x1 dot, right? So x1 dot equal to x3, that is equation. So when you are taking the second derivative of this equation, you can write it as x1 double dot equal to x3 dot. Okay, so now you have the x3 dot equations. How will you get x3 dot equation? x3 dot equation is obtained by first derivating this equation. So you can put this, you know that this is x3 dot equal to x1 double dot. So you can put this equation, see this is x1 dot equal to x3 and x1 double dot equal to x3 dot. You can put this condition in equation 561. See, we have now x1 dot equal to x3, that is the first condition, and next one is x1 double dot equal to x3 dot. You are putting these two conditions in the equation 561. So that is the rest of the equation, that is x1 double dot plus x1 dot equal to 2x2 minus 2x3. So when you are substituting, you will be getting the equation as x3 dot plus x3 equal to 2x2 minus 2x3. So you can write x3 dot directly from this equation, that will be equal to 2x2 minus 3x3. So now you have three equations, that is in terms of x1 dot, x2 dot and x3 dot. You can write it step by step. So from this equation you can write the state model. Okay, that means this is the state equations. So you can write this state equation in terms of matrix form, that is x1, this constitute a column matrix s1 dot x2 dot x3 dot, and next is you need a system matrix that is obtained from this term. In the first equation x1 and x2 are missing, so you can put 0 0. x3 is there, so put 1 because the quotient of x3 is 1. And in the second row you can put minus 2 minus 3, and here x3 is absent, so you can put 0. And here but the u term is present, let us write it in the next section. Okay, x3 dot next x3 dot equation, x1 dot term is x1 is missing, so you can put 0, next term is 2, next term is minus 3. And this constitutes the system matrix, that is A. Actually the form is x dot equal to ax plus bu. So A is obtained, x is x1 x2 x3 plus b is, what is b? The quotient of u matrix. So here there is no u, so you can put 0. Here there is a u, its quotient is 2, you can put 2. And here quotient is 0, so you can put 0. So now you will get the state model by using state equation. But in order to complete the state model, you need output equation also. What is the output here? In the question, output is x1 of s, right? So x1 of s is the output. You can directly write y equal to x1. That is your equation. Y equal to x1. Sorry. Y is equal to, your output equation is y is equal to x1 of s, and in order to get the time domain equation, you can take the inverse Laplace transform, so you will get y equal to x1. So from that equation you can write the matrix form, so you will get output equation. So actually what is the form of y? Y dot equal to cx plus du, that is your equation, and here y is independent of the input u, so you can directly write y equal to, first is c matrix and then x matrix. X matrix contains, you know that there are 3 variables, so you need to write 3 terms x1 x2 x3, and c matrix is, what is c matrix? 1 0 0, because x2 and x3 terms are absent here. So y equal to 1 0 0 x1 x2 x3. So this is the way you are writing the state equations and output equations from the block diagram. Okay, what all steps are done here is, first of all you have to identify the state variables, and you have to write the equations for state variables, that will be in the S domain form, and next you have to find out the time domain equations, and you have to make necessary rearrangements to get the state model. Also you can write the output equations so that you will get output model. Okay, so that you will get output equations from the state equation and output equation, you will get the state model. So this is the state model. And but your requirement, you are asked to find out, check the system for controllability and observability. Okay, so you can either use Gilbert's test or Kalman's test. Here for the familiarity of the test, I am expressing first, I am using first Gilbert test, then we will go to Kalman's test. So but first is the Gilbert's test. So in all the tests we need system matrix, this one. Okay, so in the case of Gilbert's test, actually what we are going to do is, we are transform. See, you can see here that in this case we have to transform this matrix or state model into canonical model, and here before that, first of all you have to check the eigenvalues. Okay, then only you can proceed. Okay, so the first value is, first step is to, you have to, in order, before applying the test, you are finding the eigenvalues. So first of all you are taking the system matrix A. What is system matrix? 0 0 1 minus 2 minus 3 0 0 2 minus 3. Okay, so this is the system matrix. So in order to find eigenvalues, you are using characteristic equation lambda I minus a equal to 0. You are finding the determinant. So you will get that determinant value will be equal to, you can see here, that will be equal to this equation. Okay, that is simply substituting, that is lambda is lambda itself, I is here 3 by 3, since A is 3 by 3 matrix, I is also 3 by 3 matrix, which is a unity matrix, minus A is this matrix. So you will get this equation. Okay, and the next step is, you want to find out the solution for this equation. So that is simply, first this is a third order equation, first you are simply putting different values, so that will be a root. Whenever you are getting 0 for the characteristic equation, then that will be a root. So here when you are putting lambda equal to minus 1, you will get a 0. So lambda plus 1 is a root. and the rest of the term is obtained by this method. Here that I have explained the previous classes, lambda equal to minus 1, we will put the 1 as it is, then 1 and minus 1 is multiplied and the result is putting here, then this will be added, so we will get 5 and minus 1 is multiplied and it is putting here, and we will add these two terms, so we will get 4 and minus 1 is minus 4 and 4 will give you 0. So the rest of the equation is lambda square plus 5 lambda plus 4, that is written here. And you know that what is the solution of this equation, that is lambda plus 1 and lambda plus 4. So now you have two roots which are similar, that is lambda equal to minus 1 value is repeating, that means eigenvalues have a multiplicity. Okay. So here the eigenvalues are not distinct, two eigenvalues have a multiplicity, that is lambda equal to minus 1 is repeating twice. Okay. So lambda 3 is equal to minus 4. So next step we want to test the observability and controllability. So we are using Gilbert's test. In the case of Gilbert's test, there are two cases, case 1 and case 2. Here the eigenvalues have multiplicity. So we are using case 2. That means we have to convert this state model into Jordan canonical model. Okay. In the case 1 we are converting the state model into canonical model, but in the case 2 we are converting it into the Jordan canonical model. You know the equations for the Jordan canonical model, that is here. In the case of Jordan canonical model, we can write it as we need, see the equation is z dot is equal to jz plus b cap u and y dot equal to z cap z plus du. This is our equation. We need this equation. So before that you need j. What is the value of j? J will be equal to m inverse zm. See, j will be equal to j will be equal to m inverse am, not zm. J will be equal to m inverse am. What is m? M is modal matrix. So in order to test by Gilbert's test, you need first the modal matrix. Okay. So our next step is to find the modal matrix. You know that if the system matrix is in the bush form or companion form, you can easily write the modal matrix. See here, the system matrix, is it in the companion form or bush form? It is not in the companion or bush form, because in the case of companion form, these two entries should be 0 and this will be 1 and this will be 1. So it is not in, also the last row will have a negative quotient of the equation. But you can see here that it is not in the companion or bush form, so we cannot directly write the modal matrix. So we have to go for lengthy procedure. That means again we have to find out, in order to find the modal matrix, we have to find out the cofactor elements corresponding to the first row of system matrix, and we have to write the modal matrix. Okay, so let us see. First of all, we have to find out the eigenvectors for finding the modal matrix, that is for corresponding to lambda 1, we can write the eigenvectors as lambda 1 I minus a. So lambda 1 and I is written here and a is here. So this will give you this matrix. Okay. So you need to find out, in order to find the modal matrix, first of all what you want is you need to find the cofactor elements, that is along the first row. So first row, this is C11, this is C12 and this is C13. So you know, so how can you find a C11? C11 equal to plus 1 into, you have to eliminate this row, column and this row. So rest of the matrix is this one. So you have to find the determinant. So you will get this equation. Similarly C12, this sign is minus 1 and C12 this and this will be emitted. So you will get 2 0 0 lambda 1 plus 3. That is the here written here, and that will give you this equation. And next is C13. So you will eliminate this row and this column. So the rest of the matrix is 2 0 lambda 1 plus 3 minus 2. So this is minus 4. So corresponding to lambda 1, you have a C11, C12, C13 right here. So you can write the, in the modal matrix, first element is M1, that is C11, C12, C13, that you will get this equation. Here you can put lambda 1 value. What is lambda 1? Lambda 1 is equal to minus 1. So you will get the matrix 4 minus 4 minus 4. And here you know that in order to find M2, you have to do the same procedure, but you know that here lambda 1 is repeating, that it has a multiplicity. So you can directly write M2 by using the equation M2 will be equal to d by d lambda 1 C11, d by d lambda 1 C12, d by d lambda 1 C13. So that is the easier method. So you don't go for the same procedure. So in the case of multiplicity, M2 will be equal to this matrix. Okay, so you will get the model matrix entry as 2 lambda 1 plus. See here what is C11. C11 have an equation in the previous step, this one. So when you are taking the derivative, first derivative, you will get 2 lambda 1 plus 6. That is written here. Okay. So in the second entry is d lambda 1 by C12. C12 is here minus 2 lambda 1 minus 6. So taking first derivative, we will give you minus 2. So minus 2 is written here. Okay. Similarly, you can find other derivatives. So you will get this. And when you are putting the value of lambda 1 as minus 1, you will get 4 minus 2 0. So you can find m1 and m2. So in the case of multiplicity, m2 is find out by using this equation. That is the point you have to remember here. Similarly, you can find the lambda corresponding eigenvector or the corresponding model matrix for lambda 3. So you can directly substitute lambda 3 as minus 4a, and I is identity matrix, A is the system matrix. So you will get the matrix like this. And again you have to go for C11, C12, C13, that is cofactor elements you have to find out, and you have to put it in the form of a column matrix. So you will get M3. Then you can write the model matrix by matrix M1, M2, M3. So model matrix is given by, that is here we are going to do is finding the Jordan canonical from. So first we need model matrix, that is M1, M2, M3. M1 is this one, M2 is this one, M3 is this one. Similarly, in order to find the J value, J will be equal to M inverse AM. So M inverse quantity we need. Here we got M value, M inverse. How can you find out M inverse? That will be equal to cofactor of M transpose by determinant of M. First of all, we have to find a cofactor of M. That is a lengthy procedure. We need to find the cofactor elements corresponding to each and every element. So we have to adopt the previous step, and then we can transpose that matrix. Also we need determinant of M. So determinant of M is find out here, and here the steps for finding the cofactor matrix is not written. Directly writing the cofactor matrix here, because it is a lengthy procedure. You can do it in your notebook. So cofactor matrix, first of all you have to in the case of 4 cofactor matrices, you have to eliminate this column and this row. Okay, so you have to find out this determinant value. So for in the case of second element, you have to eliminate this, and you have to find the determinant. So like that you have to repeat for all these entries, and you have to put associated signs, and you will get a cofactor matrix. And a transpose of this cofactor matrix is obtained by interchanging the rows and columns. So here 8 minus 24 minus 8 is the first row, so it will come to the first column, that is 8 minus 24 minus 8. Second row is 16 minus 12 minus 6, it comes to the second column. So actually what we are doing is we are transposing this matrix. Okay, so now we get numerator and denominator. So M inverse can be easily find out by using this equation. And next we have to find out the product of M inverse AM. Okay, so J will be obtained by M inverse AM. So you can put this value here, and you can multiply, that is simple matrix multiplication process. You can write it. See here is the Jordan. Finally when we are multiplying this, we will get this block like this, and here you can see that here minus 1 1 0 minus 1. So this is the Jordan block. You can see that here this is lambda 1, this is again lambda 1, this is lambda 3. Here lambda 1 and lambda 2 are repeating, that is shown here. So this represents the Jordan block. Okay, so similarly we find out J. Next we want to find out, we know that what is the form of Jordan matrix, what is the form of the canonical Jordan form, that is Z dot equal to JZ plus B cap into U. We need to find B cap. What is the value of B cap? B cap equal to M inverse B. M inverse we find out B, we can substitute, so we will get the entries like this. Okay, and next what is our need is we need to find a C cap. So C cap is equal to C into M. Model matrix we have, a C matrix also we have. What is C matrix? C matrix is obtained from the state model C. What is state model? C is, this is AX plus, this is AX plus BU, and this is plus CX. Okay, C is 1 0 0. So you can put 1 0 0 here, and this is M matrix, so you will get this entry. So next is you are applying the Gilbert's test. In the case of Gilbert test, they are looking for the matrix B for checking the controllability and matrix C for checking the observability. Okay, see here the B matrix is this is see, this is the canonical form, and you are applying set dot equal to set 1 dot set 2 dot set 3 dot, and J matrix is you have obtained. What is J matrix is, this is J matrix. Okay, you can write it as J matrix is -1 1 0. This is the matrix. Next set matrix is set 1 set 2 set 3. B kappa matrix is this is 1. So B kappa you have written and U is written, and output equation is Y equal to C kappa Z. So C kappa is this one, and Z is written. Du is not here, defined here, that is why. So first of all, in order to check the controllability by using B kappa matrix, it should not have a all zero row. That is the controllability test. Here you know that there is no all zero row. All rows will have some numbers. So you can directly say that this is controllable. So it is observed that the elements of the rows of B are not all zeros, hence the system is completely controllable. Next, by using the Gilbert's test, you can check the observability. Here it is given that in the case of observability, we are checking the C kappa matrix. Here you can see C kappa matrix is this. Here all columns we are checking, columns are non-zero. So we can say that it is observable. So it is observed that the elements of the columns of C cap are not all zeros, and the system is completely observable. That is, all the state variables are observable. Okay. So this is a Gilbert's test. Next we can apply Kalman's test also. Let us see. Kalman's test condition, you know that this is, first of all, we have to form a composite matrix, that is QZ is equal to B, AB, S square B. Like that it will be continuing, but here you know that it is a, here the state variables are 3, so you need 3 terms alone. So B you want, and you also need AB product. What is B? B is obtained from the state model, that is B is X plus B. What is B? B is this 0 2 0. Okay. So for that every test we need a state model. So first of all you have to form the state model. Okay. So by B is given, so you can multiply A and B together, so you will get a second matrix. Next A square B, first, so you want to find A square, so A square is found here, A square B is given here. So instead of all these elements you have to write all this. Okay, QC. So next you have to find the rank of the matrix. How will you find out the rank? First of all you have to find the determinant. So determinant of this one is equal to 32. That means it is non-zero quantity. That means the order of this matrix is 3. So the so whenever the determinant is non-zero, then the rank will be 3. So both the order and the rank are equal. So we can say that the system is completely controllable. So the previous result is also controllable, and by Kalman's test it is also controllable. Next we can find the Kalman's test for observability, and here also we have to form a composite matrix, and the composite matrix is QZ. This is the composite matrix. For that we need C transpose, also the product of A transpose C transpose, and product of A transpose square C transpose. So we have the C matrix, okay, from the output equation. So what is C matrix? C matrix is this one. We need to find a transpose, so transpose will be this. And also we need A transpose matrix, so A transpose is written here. Also A transpose square we need here. The entries of Q0 is determined by the number of state variables. If it is 4, we need other terms also. Okay. So now we will obtain different terms. We can substitute for each and every terms, so that we will get the composite matrix like this. This is the composite matrix. Here also we can apply the check, and here also we want to find out the rank. For that first we are finding the determinant, and the determinant is -2. That means the determinant is non-zero. So the order of the matrix will be equal to the rank of the matrix. So rank will be equal to 3. So both are equal, so we can say that the system is completely observable. So from the analysis you can find that it is better to apply Kalman's test to check controllability and observability, because it needs less number of steps. So you can save the time. If you are asked to find the asked to apply Gilbert's test, you can apply that. If it is not asked for Gilbert's test, you can directly apply Kalman's test. Okay, that depends upon the questions, and you can save time by adopting Kalman's test for controllability and observability check. Okay, that's all about this problem. Thank you.